kindness. Thanks for doing all your.
Thank you. Thank you for having me here.
Yes, I forgot to, I was just going to tell you. Yeah.
He's doing really nice work on checks.
Is it? Or-
No,
Right, he wants to copy. Right, hopefully he can.
Okay.
Okay, let's go ahead and get started, everyone. So it's my pleasure to introduce Vera Matarese. Vera is a professor of philosophy of science at the University of Sicily in Italy. She's written on a wide variety of topics, from the metaphysics of Fermion mechanics to the Hubble constant controversy, which we'll hear about tomorrow in Foundation Seminar. If anybody is free to join, that'll be at 9:30 tomorrow. I've had the pleasure of working with Vera on an edited volume on the philosophy of astrophysics, which was really great and fun. So please join me in welcoming you here.
Thank you. Thank you. Well, thank you all for being here today, and thank you for having me. Thank you, Helen, for inviting me. And so today I'd like to discuss with you about this question of whether we should be realist about dark energy or anti-realist. So, okay, so now it's not working. Okay, so then the question is not only whether dark energy exists, and so it's in the set of things that physically exist in this world, but also whether we are justified in committing to the existence of dark energy, and so whether there are compelling arguments that really support the claim that dark energy exists. So you might actually want to challenge the significance of this question and say, well, look, our best science, the best cosmological model we have, the ΛCDM model, introduces and posits this entity, dark energy. But of course, we know that we do not have empirical proofs that really confirm the physical existence of dark energy. So we have, of course, to wait until there is an empirical proof. But the problem is that from a philosophical perspective, even deciding when we are allowed to answer the questions of the ontology, and so whether dark energy exists, is actually occupying a particular position from a philosophical point of view. Why is it so? Well, because the scientific realism claims that science tells us the truth about the world, the universe, the physical reality where we are in, okay? And it tells us the truth regarding both observable entities that can be empirically accessible and non-observable ones, okay? So even those entities that are not empirically observable, okay? And if we think that we have to wait until we get an empirical proof about the existence of dark energy or any other non-observable entities before being able to actually answer this question, then it means that we are endorsing scientific anti-realism, which is a kind of philosophical view that is not really appealing, okay? It would tell you that science does not tell you the truth about the world. It just tells you that we should not believe in scientific theories because they just give you predictive success and not really telling you about the world. So we don't want to do that, right? So, of course, the scientific realism is not that naive. It doesn't tell you that we should believe in all entities that science posits in their theories or models. We have to ask and check a few things. For instance, we have to check whether our theory or model is mature enough, or whether it is successful, okay? Whether there is an underdetermination problem. Are there other models that are alternative to the one you're actually investigating, okay? Is the entity that you want to find out whether it truly exists in the world really indispensable for the model you are examining, okay? And then suppose that you say, well, no, this entity actually does not exist. Then it would make sense to explain the progress of the theory or model that you are endorsing. So suppose that you have a model that is progressing, okay, that's made really great advancements, okay. If the entity that your model postulates did not exist, would it make sense that this model or theory really made a progress. So there are all these questions that we should ask if we want to find out whether we can be a realist about dark energy. Is the lambda CDM model mature and successful? Is there an indetermination problem for the lambda CDM model? And in case dark energy did not exist, can we make sense of the progress and the success of the lambda CDM model? So then the plan for today is that I will very briefly introduce the dark energy and then focus on what it means to endorse dark energy realism. Then I will propose some arguments in favor of dark energy realism and some arguments against dark energy realism, so that would endorse dark energy anti-realism. And then I will propose my own view, which is dark energy fictionalism. So the lambda CDM model is the model that has introduced the dark energy, okay? And it's based on a pretty well understood Einstein's general relativity, okay? And a pretty well accepted Friedman, Lemaitre, Robertson, Walker models, okay? So the lambda CDM model is called the concordance model because it fits.
Yeah, but
Yeah.
you're framing the whole discussion as if there might be a yes or no answer, aren't you? So what about people, perhaps which would include myself, that would say, we're not sure exactly what we mean by dark matter in sort of the broadest definition, and you have an equation where there's a term missing, and whatever supplies that missing term is dark matter, and also that it might be true or it might not be true. What?
Yes, so we will exactly discuss this view also. So the standard, normally philosophers frame the debate, okay, in this way, so that there is a yes or no question. In case you have a successful model, okay, a mature model that posits an entity like dark energy, okay, then are you in favor of being realist of this model or no? And this is a yes or no answer. But then we will see that dark energy fictionalism actually takes into consideration your point of view. That we don't even
have a provisional model.
Yes. Yeah.
Yeah.
So in case you have a provisional model, exactly, you can't say that it is entirely mature, okay, because it's provisional. Okay.
At some level, on almost all scientific models provisional,
Yeah.
they're best to date.
Well, there is, however, a kind of, limit, okay? So there are some models that we could say, well, look, of course, we know that science keeps progressing. So as you may want to say they are all models that are provisional. But a scientific realist would say, well, I'm not saying that science tells exactly the truth, okay? Approximately, it tells you the truth. And then the more science progresses, the more it tells you the truth, so that it's closer to the real truth, the perfect truth, okay? But we are driven by truth.
So quick follow-up before I let you
Yeah.
continue. So, lambda CDM is, would you call it a mature model or theory, despite the fact that it has these two very provisional entities, like Andy said, even dark matter, we don't know what it is, and dark energy, we don't know what it is.
Yeah,
Does
we-
that
this
impact the
is
authority of the
yeah.
model?
This is exactly what I will discuss like into 3 slides. So whether we can actually say that the lambda CDM model is mature and successful, despite the fact that we don't know anything about, and so that there is an underdetermination of what the nature of dark energy is. Yeah, so I think that we are agreeing on the final kind of thought.
I think we
Yeah.
understand your terms, but, I think I understand you better. But
Okay. Good, yeah. So scientific realism tells you if you have a, you should believe in science. Science tells you about the truth, but of course it's not naive, okay? So it tells you, well, you should get your best science, okay? It seems that the lambda CDM model is the best science that we could get now, okay? But then is it really a mature model, okay? So then we will be discussing this, okay? Is all
You should
fine?
keep going.
Okay.
If you give us rope, we'll.
Okay, okay, so, well, exactly, so we are saying that according to the lambda CDM model, even 70% or so of the universe is filled out with dark energy, okay? And then we know that dark energy is required as an extra ingredient to balance the density of the universe and also to account for the accelerating expansion of the universe, okay? We also know that most probably does not clump together under the influence of gravity. It's not, it does not influence, it's not influenced by matter, and that is smoothly distributed, okay? We know that in order to balance the density of the universe, and in order to account for the accelerating expansion, it also needs to have a positive energy density and a negative pressure because it has to account for a repulsive force, okay? We also know that most probably when the universe was younger, then it was a pretty significant component of the universe. Well, now it should be like 70%, okay? So now we go into dark energy realism. What does it mean to say that I'm a realist about dark energy, okay? So it is an epistemically positive attitude toward dark energy, okay? And it is grounded by the fact that the lambda CDM model is successful, okay? So the main claim is that dark energy is physically existent, okay? Even though it is not observable, okay? And so the lambda CDM model not only fits the majority of observation, okay, not only is a great instrument, okay, that we have, but it has a genuine literature true content, okay, so it refers, its terms refers to the word, okay. And then if in 20 years we find out that dark energy does not exist, that would falsify the model, okay. So normally scientific realism has two different components, okay? So it tells that mature scientific theories or models have their terms that refer to the word and that they tell us approximately true things about the world, okay? And the second component is that this claim is the only way we have to explain the success of the model or the theory, okay? Otherwise, that scientific model, okay, would be a miracle, okay? It would be a miracle that we have a model that is successful and yet it does not tell us anything about the truth of the universe, the world, the physical reality, okay? So for dark energy, okay, the semantic component is, well, dark energy, the term dark energy really refers to something in the world, okay? And then the only argument that we have to explain this, okay, is, and this is the only argument we have to explain the success of the lambda CDM model, okay? If a dark energy did not refer to anything in the world, then we would not be able to explain the success of the lambda CDM model, okay? So we could see also the thing the other way around, okay? The best explanation for the lambda CDM model success, okay, is that the model's entity are actually instantiated in the world. They are in the world, they exist in the world. And the predictive success, okay, of the model justifies dark energy realism, okay? It's the best explanation for the lambda CDM model's predictive success, okay? And then the semantic components makes more precise, okay, what does it mean that the model's entities are instantiated in the world? Well, it means that dark energy exists, also called dark matter and other things, okay? So then the two components together would form dark energy realism. So as you can see, okay, scientific realism is intrinsically connected to a naturalistic attitude of a philosopher of science who have the desire to ground their metaphysical commitments in science and in our most successful scientific models and theories, okay? So a philosopher of science with a naturalistic attitude would say, well, given a successful theory or a model, what does it tell us about the world, the universe, the physical reality, okay? But then the problem is, well, is really the lambda CDM model successful and mature? Are we justified in believing in being realist of the lambda CDM model? So the first thing to say is that the lambda CDM model is called the concordance model after Osterker and Steinhardt papers in 1995, a cosmic concordance, okay? And it was called like this because it fits the majority of observation. But a philosopher would see two peculiar things. So the first is consistency. So as in their paper they are saying, Osterker and Steinhardt, well, we have so many different constraints by measurements of the angular size of fluctuations of the CMB, the larger scale structure, the Hubble constants, and so forth, and so on and so forth, that they are all consistent with that model. Okay, but then more strongly, Turner in his 1997 paper says, well, actually, all these data on the CMB, data on matter clustering, density, the Hubble constants, the age of stars, and so on and so forth, they actually rule out all available models, of course, at his time, okay, as they are consistent only with the lambda CDM model. So it's all, the claim is stronger because it says that all the data available so far are consistent only with the lambda CDM model, okay? A philosopher of science would also see robustness. And we do have robustness whether we can actually use different lines of evidence that are pretty independent to arrive at the same model. They all support the same model. We have a robustness when removing any single piece of evidence would actually reduce the accuracy of our parameters, of the cosmological parameters that we know. We do have robustness when, if the model would be wrong, then it would really be a conspiracy, okay? And this seems that is actually what's happening with the lambda CDM model, that, we have consistency and robustness. But then, wait a minute. So we were saying, okay, that the only way to explain the success of the lambda CDM model is to be a realist about its semantic components, okay? But then what do we mean by success? Normally, scientific realist talks about predictive success, okay? So when a model has predictive success, it is confronted with new data, then it is predictively successful, okay? So what about the lambda CDM model, okay? So one might wonder, does it just accommodate the data or it's really predictive successful, okay? So here the problem for philosophers of science is really to understand the difference between accommodation and prediction. So many philosophers of science worked on this, and according to someone like Mayer, a way to distinguish between the two is to talk about the temporal aspect, okay? So if we didn't have some data, okay, before developing a model, and then this model predicts some new data, and this new data comes in later on, then we have prediction, okay? If the data were known before, okay, the development of the model, then we have accommodation. So then some scientific realists might want to say, well, look, for instance, the data of the supernova, they really confirm the acceleration of the expansion of the universe came just after, okay, Turner published in a 1977 paper that, the all data were consistent with the model, okay? And then after that, we have also had the confirmation of Latinos space. We have enhanced precision in parameter measurements and so on and so forth, that they all, these are all data came after, okay? However, okay, was it really a matter of a prediction and then a confirmation or falsification? Okay, it seemed that when the data, for instance, of the expansion, the accelerating expansion of the universe came in, okay, then the lambda CDM model was really the model that could perfectly fit all of the data together nicely, okay? The properties of the CMB fluctuations, the upper constant value at the time, and the expansion, the accelerating expansion of the universe. So was there really prediction or was more accommodation? Well, let's suppose that was accommodation. Is this really a problem? Should we really say that accommodation, okay, is less valuable than predictive power? Well, some philosophers of science want to distinguish between two different kinds of accommodation. So we have accommodation one, in case some data were already known before the development of a model or a theory, okay, that then entail this data, but were not used, okay, they were not used to actually build up the model. We have accommodation too, in case the data were known before and they were actually used to build up a model that could fit this data, okay? And normally, the common knowledge is that, well, look, okay, so accommodation one is actually has the same confirmation power than, successful prediction, okay? While accommodation two is not that good, carries less weight, okay? Well, one scientific anti-realist may actually want to say that the lambda CDM model accommodates the data in the second way, okay? But would that really be so bad, okay? Well, first of all, still accommodation two is kind of good, right? I mean, tells us something positive things about a model. If a model, okay, can fit data that are real, okay, then at least it's consistent with the data we gathered, no? Right? So at least some very, very weak degree of confirmation, if we look at degree of confirmation as something like a probability or like the viability of a model, the trustworthiness of a model, that maybe can contribute a little bit, right? Then the other thing is that actually we should be honest, right? I mean, it's standard scientific practice to use data that come in to actually fix parameters values that are left free by a general framework. I mean, this is the common practice, okay? Then when we have new data that come in, okay, and with this new data, we can fix, okay, some parameter values that were left free by the general model, we can say that actually this data, okay, confirm a specification of the general framework of the model, not the general framework of the model, but a specification, a version of the model, okay? Please.
This question has been bothering me while
Good.
listening to your talk, because lambda CDM,
Yes.
as initially visualized, had a lambda, which is independent of redshift. And today, lambda CDM includes, the equation of state changing with redshift, W prime, W of A, all this stuff. So how should I view this? Should I say that this larger set of models, which include redshift
Yes.
evolution, is the model, or is this,
Yeah.
somebody is cheating? Because
Yes.
the original model, now people are saying it doesn't work. we need
Yes.
some evolution.
Yes.
So, yeah,
Exactly.
what is your picture of lambda CDM? Is it the new lambda CDM or the pure lambda CDM?
Well, I would say the new lambda CDM, but I think that you could also like apply the same kinds of argument.
When you say new, you mean including the extension?
Including the
The
extension,
extension, yeah.
where
that's right.
to me, it looks like you're making an
Okay, so-
excuse.
So just so let me clear, I mean, of course, the lambda CDM model had this, evolution. I mean, to me, it was still lambda CDM before this new data come in, okay? So Turner and, Steinhardt paper do not really say like lambda CDM, but I would still say that this is a lambda CDM. Okay, but then of course it evolved and now we know that it's talking about acceleration, accelerating expansion of the universe. Okay, so for me, it's all lambda CDM that had this evolution.
Okay.
Maybe a quick follow-up.
Yeah.
How do you know when your theory is mature enough to make that claim? Like, I'm sensing the idea of being at the initial,
Yes.
like at the outset, it
Yeah.
wasn't mature enough to be
Yes,
making evaluations.
Exactly. So for sure, yeah, thank you. So for sure in 1995, it was not mature enough. Okay, there were still different models at stake at the time. There was great uncertainty. We didn't have the knowledge, the confirmed knowledge that there was an accelerating expansion and so on and so forth. What about now? I mean, are there some criteria that you can apply for all cases in a rigid way? I don't think so. I think it's a more matter of like looking case by case. Okay, and this is what we are trying to do now. Okay, so here I would like exactly to do this. Okay, to see case by, in this particular case, whether there is a yes or no answer to the question of whether the lambda CDM model is mature enough and is successful. Okay, so we are looking at, whether it's actually, well, if it has a truly like predictive power and, it could not be seen as an accommodating model, then we could say, well, we have some confidence that that is successful, okay? But, a scientific anti-realist might say no.
Maybe a historical note. There
Yeah.
was this debate that was organized maybe 20 years ago
Oh.
between Pavel Krupa and Simon White about dark matter.
I see.
And they talked about this. And one of the arguments that Pavel Krupa was making is, just before Newton,
Yes.
we had this beautiful theory based on epicycle
Yeah.
that assumed that everything was moving in circles.
Yes.
That could explain all the data.
Yes.
And when new data came
Yeah.
along that didn't fit, we just added a level of
Yes.
epicycle
Exactly.
and it would fit
Yes.
again.
Yeah.
But yet that theory that we had before was completely wrong.
Yeah.
It just had so many free parameters
Yes.
that you could
Exactly.
basically explain everything.
Exactly.
So I think the question to me at least is this lambda
Yeah.
CDM model like this, that it has so many things that you can tweak. that-
Exactly.
that
Exactly.
You could
Yes.
explain anything.
Yeah. Exactly.
That's kind of what I was gonna say. I was just gonna say, hasn't history taught us that all our models, we should never be too sure they're mature, and we always check with data when we get new finer grained data and try to adjust our model to fit it and keep doing that until something comes that is a paradigm shift that actually has something, a clash with the previous model, then it becomes supplanted. But until then, we are always never sure we're
Yeah.
sure.
But then,
Isn't that
so
how scientists
this
generally do it?
attitude is extremely cautious, okay?
I mean,
And, it's by what philosophers say, the meta-induction reasoning, this is what we all should believe, okay? So history taught us we should not be realist about science, okay? But this is, of course, not something that we can endorse, right? We can't endorse this, that we should never be sure about science, that science never tells us the truth about things because we have always to wait. And so we have, of course, to try to find some good reasons to be positive about science, okay? And to kind of see what are the arguments, okay? But yeah, we will go back to exactly this in like 2 slides, okay? So then if this new data, okay, that come in, okay, just can just fix a particular version of the model, but cannot confirm the overall general framework, okay, then we would be entitled to be a scientific realist only if there was just one general framework, okay? But then if the lambda CDM model suffers from underdetermination, okay, so this is the second question that we should all ask, okay? So there are different kinds of underdetermination, okay? So there is one global underdetermination. I mean, we got everything wrong, okay? The cosmological principle doesn't apply, okay? Or even, you know, more drastic things, okay? Then there are different kinds of local underdetermination, okay? It could be that there is, I don't know, no dark energy, but there is a whole dark matter, you know? Or even more local, the lambda CDM model exists, but then the dark energy exists, but then what is dark energy? As we were saying before, we don't really know, and there are different models of what dark energy exists. And this is what we will very quickly survey now, okay? So of course, many different proposals of dark energy were offered, right? We do not know the nature of a dark energy, okay? And there are so many different possibilities. That is the lambda constant, that is a kind of quintessence, that is phantom energy. I mean, there were so many different proposals that were made, okay? So then if we're a scientific realist, okay, and we say, well, okay, so suppose that this model provides, tells us the truth about the world, the universe, and then what would be the universe, okay? What would be like? We don't know. I mean, we don't know what dark energy is exactly, okay? So then we don't know what we are realist about, okay? It's just a name, dark energy, okay? So it could be like the lambda constant, but then in the sense of Einstein was saying that's a property of space, or in the sense that it's a vacuum energy, okay? Of course, that's a constant energy density to the universe, but it's a consequence of the quantum mechanics uncertainty principle. But then, of course, this has this problem, right? That if we try to calculate, then it will be 10 to the 120 greater than it actually should be. So, of course, this is a problem. It's a quintessence going back to Aristotle's notion of this strange energy, or sorry, substance that fills us the universe. Well, then how we would characterize it? It's a scalar field, a quantum field, okay? That has negative pressure that varies with time, decreasing as the universe expands. Is it a phantom energy? But then we will not even know how exactly it develops, okay? It can escalate and become a big read, or it can actually cause a big crunch, okay? We don't know, okay? There are all these different options. And so the problem is that we cannot run an eliminative or causal argument that would tell you that, okay, if you can run this argument, there is no underdetermination problem, okay? So this is a typical argument for philosophers that say, well, look, okay, given what is known, there are possible causes for, I don't know, the accelerating expansion of the universe, okay? So there are some effects, the acceleration, and there are some causes, okay? The lambda constant, okay, quintessence, phantom energy, okay? But then, you know, I don't know, phantom energy and quintessence cannot actually cause the acceleration of the expansion of the universe. So probably the lambda constant would, I don't know, in the form of vacuum energy, for instance. But then we know that we cannot run this kind of arguments, and so that we do have a local underdetermination, okay? So a scientific realist would say, well, come on, don't worry too much. We cannot really tell exactly what the properties of dark energy are, okay? But just adopt some descriptive opportunism, okay? So this concept was applied in other fields of philosophy of science, but now I'm applying here. So use some pragmatic criteria. As long as you can reason well in the presence of dark energy, okay, then you should be realist about this, okay? So can we do that for dark energy? I mean, well, it seems that we can reason well about what dark energy could be, and we have different models, okay, that are constrained by some data. But can we really reason well and properly in the presence of dark energy? Well, if we don't know what it is and the full specific properties, okay, of the dark energy, then we cannot reason properly in its presence, okay? So then we can say, okay, we do have a local underdetermination problem, but look, we always have a local underdetermination problem. Do we really know what electromagnetic fields are? Are there like physical fields or like nomological entity that are shown in our laws of nature? Philosophers are still debating this, okay? So then we say, okay, well, maybe we have good reasons, okay, to maybe look at the global underdetermination, not the local, that, you know, every physical model has a local underdetermination. Well, normally you would not have a global underdetermination problem if we can run a non-alternative argument that was applied by Richard David for actually another kinds of underdetermination, okay, that by some sort of coincidence was called the local, but for other reasons. But here I will apply this to the global one, okay? So the argument is the following. Look, if scientists have looked, okay, for alternatives, okay, and you know, after some period of time, no alternatives were found, okay, that's an indication of the viability of your model or theory or hypothesis, okay? So are there alternatives to the lambda CDM model, okay? Could other hypotheses, okay, receive as much support of the dark energy hypothesis going beyond the lambda CDM model? Well, there are some astrophysicists that are working on alternatives, okay? So for instance, Chiavone, Montani, and Pasten, and Cardenas are working on the LTB model, Lemaitre, Tolban, Bondi model, okay? So models that deny the cosmological principle. They actually retain isotropy, but they deny homogeneity, okay? So they say, well, look, okay, maybe there are some spatial variations in the distribution of matter in the universe, and we might be occupying under dense region, the Hubble bubble, okay? So that is the real expanding, okay, at a faster rate than average, okay? But then our lambda CDM model would be flawed, okay, because it's assuming a homogeneous FL or a double view model, okay? If a realist might say, well, okay, I mean, there are always some alternatives that you can find as crazy as you want. But then, I mean, you should use some background information when you judge whether the alternatives are good enough, okay, or they are plausible, viable alternatives, okay? So as long as with some background information, okay, you rule out all but one, okay, then you do not have a global underdetermination. Okay, so what would this background information be? Okay, so supporters of dark energy, so dark energy realists might want to say, well, you know, the lambda CDM model actually is the standard cosmological model. It's the only model that we reasonably have so far that we have been working. If the whole science, almost all the scientific community is putting efforts on this model, there must be a reason, okay? Then the anti-realist about dark energy would respond, look, First of all, the lambda CDM model is a fitting model. It just accommodates the data, okay? No predictive power. Then the lambda CDM model extension, and Leonardo Di Valentino last week was telling you about the Hubble tension, okay? Then there are also other alternatives that have not been seriously investigated for social reasons, not for scientific reasons, okay? And then some characteristics of the model, the lambda CDM model, makes us suspicious of its realistic character. And so that it actually does not represent reality. What would these characteristics make us suspicious? So there are some philosophers of astrophysics who have been working on cosmological astrophysical models. And so models with a scarce observation, okay? And Rufi, in her paper in 2007, really individuated two different characteristics that all these models have, or most of models have, which makes us suspicious about the realistic character. So the first is plasticity, okay? So plasticity is what you were saying before. It's like the possibility of adjusting the ingredients of the model, okay? So that it remains empirically successful as new data come in. And this, of course, requires that we incorporate new structural components in our model, okay? And then the more data come in and the more we adjust the model gets rigid, okay? This process rigidifies the model and makes it stable, okay? But it's not stable for predictive success. It's stable because you keep adjusting the model, okay? The second characteristic is a path dependency, okay? So, which is that in this process of adjusting the model, you never go back and question, okay, the last step, okay? But every decision is path dependent, okay? So basically it depends on the previous decision that you made as a new data came in before, okay? And then for the future data, you have to start from the position where you are, acknowledge, okay, the path that you took, okay, and then move forward and make the second, a further decision, okay? So this is an adjustment, okay, that again creates the stability of the model, okay? But it does not really give you the space to go back to the first and change a route, okay? And this is sometimes what happens, okay? So then the dark energy anti-realists might say, well, look, also the lambda CDM model, okay, suffers from this, and then this suggests a non-realistic interpretation of the lambda CDM model. We do not have a stronger falsifiability in this kinds of model, okay? And so we should not be realist about the lambda CDM model, okay? So this is, of course, a serious problem. Why is it? Because actually, astrophysicists and cosmology build up models to know what the world is like, the universe is like, okay, the physical reality is like. So if their models, the majority of them have a path dependency and plasticity, then, it would be really, probably would cause a tension between the epistemic goals and what they get from the model, okay? And also, the more complex the model is, okay, then the more you lose the control of your validation. So for the lambda CDM model that is very complex, then you lose control of its validation. But then dark energy anti-realists would have a terrible problem because, well, look, okay, 70% of the universe, according to the lambda CDM model, is filled with dark energy. And we cannot be realist about dark energy. We can also not be realist about the lambda CDM model because it has this feature, okay? But then, I mean, what about the whole cosmology, okay? I mean, the most important achievement that we go so far is the lambda CDM model. So then does it really open to the possibility that we should not be realists of cosmology. It seems absurd, okay? Because now we finally have a scientific cosmology, okay? And it seems absurd that we cannot actually account for the progress of knowledge that we had so far, okay? So actually the scientific anti-realists are on a slipping slope, okay? Slippery slope, okay? So then they're not realists of dark energy, they're not realists about the ΛCDM, and then what about cosmology, okay? How can they stop their anti-realist commitments? So this is what we got so far, okay? Well, let's say that we do not have entirely compelling arguments for dark energy realism, but let's say that also dark energy anti-realism would really be too catastrophic, okay? We don't want that. So let's go for my proposed solution, which would be dark energy fictionalism, okay? So as I was saying before, it seems that, you know, the whole debate is yes or no, okay? But there could be a middle way, okay? So don't be too much negative about this term of fictionalism. It's a term that we use in philosophy of science, okay? So for us, a fiction is any narrative, also scientific narrative, and narrative is a positive term. It narrates, okay? A narrative of what is not empirically accessible in order to understand what is empirically accessible. So it's a kind of, it can be an entity, but it can also be a whole model, okay, that we introduce to explain, okay, what is empirically successful, okay, what it can be empirically observable, okay, reachable, okay, but then introducing, it is introducing something that it's not empirically accessible. Okay, fictionalism has been employed in the philosophy of science quite widely, also in philosophy of science, to explain the status of scientific models. They are fiction, okay, and also to talk about particular entities such as the ether, okay. So Maxwell ether, okay. So it thinks that then turn out not to exist, okay. But also to talk about entities, okay, that we posit, okay, but then they could represent or may not represent something physical, okay. So I will try to contend that we need a fictionalism to understand dark energy. So first of all, because of fictionalism is extremely fruitful for troublesome entity, okay? So why is it so? Well, troublesome entities are entities about which science talks about, or it could also be like our common parlance, you know, we commonly talk about them, okay? But then, you know, when philosophers question you, then, you know, here there are some, you know, troubles, okay, or some scruples that prevent you from actually committing to their existence, okay? And the fictionalism gives you the metaphysical space, okay, in which you can talk about troublesome entities, okay, but then you're not compelled to endorse the existence of these entities, okay? Of course, a dark energy is a troublesome entity, okay, because we saw before how many arguments, okay, might tell you that we should not commit to the existence of a dark energy, okay. Also, it does not have an empirical proof, it's empirically inaccessible, okay. Also, there is a proliferation of different alternatives of what dark energy is, it's obviously under determination problem, and so on and so forth. Okay, so it's really challenging to break this severe underdetermination, okay, by theoretical or empirical means. So then we should employ fictionalism. And attention, this does not mean that we should discard dark energy as a non-existing entity. This does not mean that we are saying, oh, dark energy does not exist physically. It's just a fiction. No, dark energy for sure exists qua a fictional entity, okay? Because it is introduced as the best possible candidates of physical reality in our best scientific model that we had so far, okay? It is introduced as a possible entity that could be in an isomorphic relation with some physical entity, okay? We should be realist about dark energy in the sense that we should really think that dark energy exists a quite fictional entity, okay? Because of a famous philosophy argument, the prime pattern indispensability argument that tells you, well, you know, if for your best scientific model, an entity is indispensable, then it must exist. And it's not talking about physical existence, okay? Could be like mathematical existence, okay? But it does exist, okay? Dark energy is indispensable within the lambda CDM model, okay? And we can safely talk about dark energy in an objective way, okay? It's not something that is being created, okay, in my mind and I cannot share with you like a dream, okay? But no, it can be articulated in a scientific, objective way, okay? And the knowledge of dark energy can grow further in an objective way, okay? It can also account for explanation, okay? Why is it so? Well, if you have some background information like B1 and B2, okay, and if you hold some properties, some fictional conditional here, F1 and F2 about the dark energy, okay, then you could derive measurable properties of the target system, okay? So you can put fictional entities in your explanation, okay, of truly existing things in the world, okay? Fictionalism also embraces underdetermination, okay? So it's perfectly compatible with the fact that we have an underdetermination problem because dark energy is a fictional entity. So you can have different narratives, okay, of what dark energy could be, okay? And then most importantly, it's not anti-realist. It does not conflict with the scientific realism, but at the same time, it's not naive, okay? So we know the science talks about reality and, okay, we need a scientific fictionalism. That is, we need this realistic attitude towards a fictional entity, okay, because science is truth driven, okay? We know that dark energy is a promising candidate for physical reality, and so we should believe in its existence. Maybe for now, we can say that it's fictional, but it may or may not be in an isomorphic relation to a physical entity, dark energy, okay? So then we do believe in the existence of empirically inaccessible entity, non-observable entity, okay? So scientific fictionalism applied to dark energy is driven by truth consideration because it asks, well, you know, if this model were, if, you know, dark energy was existent, if this model really referred to the world, then could it really explain the truth of, for instance, the accelerating expansion of the universe? And in this regard, it's very much in line with the scientific realism. So here's some conclusion, okay? So I am a scientific realist, okay? So I believe in science. I believe that science tells us the truth, okay? And I think that we should not wait until empirical confirmation to decide on the ontic status of things. I believe in science, okay? But we need to not and so we did not to wait and so we do not need to wait until empirical confirmation. But at the same time, okay, we need to wait until the model becomes mature. And we saw that for the lambda CDM model, there are all these problems, okay? So then my conclusion is that the model introduces dark energy as a fictional entity, okay, to explain measurable physical phenomena and to represent possible physical candidates of reality. Thank you so much.
Okay, I'll alternate between room questions and Zoom questions.
Oh, thank you. Very
Thank
nice
you.
talk. I want to come back to this notion of approximate truth.
Yes.
It seems to me there are a lot of things, and we heard a little bit about this earlier from Andy and Priya, about what one means, what it would mean to be approximate. Something could be approximate, say, the way quantum electrodynamics or another quantum field theory is approximate in the sense that it's revised at higher energies, but in its domain of applicability, it works better. And is not approximate in that sense. There are models that might be thought to be approximate because they make an idealization in some way and simplify it for calculation. But there's also a kind of approximation that is a heuristic, like Einstein's original supposition in the existence of a photon.
Yeah.
He knew perfectly well that this was not a mature theory. And it would be another half century before, 40-something years before you had a quantum electrodynamics. He didn't know how to reconcile the wave and the particle aspects of light. He knew that both were true, but would you say that we should, I mean, suppose you were giving this talk in 1906 and the question came up, should we be realistic about the photon? Someone would say, well, you believe that you should only believe in theoretical entities when they're a mature theory, but would you really wait for 43 years till Feynman, Schwinger, and Tominaga had a Dyson had a theory, a full-blown reconciliation of this? And maybe that's the situation we're often in. We have an approximation, but it's telling us something veridical. And we believe that aspect is going to be sustained, even though the theory isn't fully mature. Now I'm not saying that this is the case for lambda CDM, but it seems to me that demanding a full-on mature theory may be too strong.
Yeah, I completely agree with you, okay? So that it's impossible, okay, to wait until a theory is completely mature, okay? And this is what also it was said before, I mean, by a meta-induction reasoning, we should actually say that we will never, I mean, as long as we don't have the fundamental theory of everything, okay, then most probably, we could say that we are discovering an approximate truth of things, okay? But this does not justify an anti-realist perspective, okay? Then the problem comes, I think, in distinguishing whether we have heuristic models, provisionary models, or models that aim to represent reality in a more robust sense. So I think that the difference is really hard to pin down. But I think, and you should tell me what I'm wrong, but I think that sometimes really some models are just there as in a kind of heuristic fashion. Okay, so we have to make a progress. We don't really know where to look, and then we come up with a series of different models, okay, that could all represent these scenarios. And then you have all these incompatible models and a plurality of models, okay, that were just a heuristic, okay? And then there is another, I think, way in which you can have a model, which I think, but I might be wrong, is more in line with the lambda CDM model, where it's not really a heuristic model, but it's a really robust model that the cosmological community is trying to build up to really explain the data and especially to represent what is out there. And so in the first sense, for really heuristic models, I would not say that they tell us approximately the truth, but they just explore. So they are exploratory models. Why in the second sense, I would say that most probably the model is telling us approximately the truth about things, the truth about things, right? So I would be more inclined, okay, to say that the approximate truth is in the second kind of model, not in exploratory or heuristic models. But yeah, it's debatable, so yeah.
Can you take one more quick question? I have some, but maybe I'll save them for
Thanks.
lunch.
Yeah.
So why don't we
Thank
thank
you.
you?
Thank you very much.
Thanks everyone for coming.